we're gonna get started. So welcome everyone. Thank you for joining us today. My name is Joy To, and I'm the Assistant Director for Strategic Partnerships at the Data Science Institute here at Columbia. So today's seminar is an iCubed, which stands for Institute, Industry, and Innovation. So these seminars connect our industry affiliates to our students and the larger Columbia community to explore topics at the forefront of industry. So we invite data scientists, engineers, or researchers to give a talk about a recent project or case study. And during these educational events, we encourage attendees to ask questions at the end of the Q&A session. So today we have Subrata Das and Mariam Kubiri, Vice Presidents and Lead Data Scientists at JPMorgan Chase, and one of your fellow students, Haonan Duan, presenting today. So thank you all for joining us.
Thank you again, Joy and Alexis, for inviting us again the second time in our speech, because this is a very exciting time to present this particular project, because we did some capstone projects with 2 cohorts of students last year in the fall semester for their master's thesis, and this is one of the projects we are presenting. And we are really excited because the amount of results we gained and the amount of insights that we have gained from this study. So again, thanks to all the attendees here, and thanks for the organizers for inviting us. This particular topic is to kind of develop a stock market forecasting model using some of the state-of-the-art machine learning and deep learning models. Not only machine learning, deep learning, but also combining this model with financial analysis, that is the Black-Scholes option pricing models, and to kind of get a holistic understanding of how we can comprehensively understand the stock behavior, the market dynamics, and use these time series models in conjunction with the Black-Scholes option pricing models to improve the stock market performance, or predict the stock market performance with improved precision. So first I would like to acknowledge apart from Haonan, who was one of the leads in the project, apart from him, there were some few other people also, Ming, Mohan, Pojen, and Li Hu, and Laurie, as the other collaborators in the project. So this particular problem is very important from business perspective for us, because as part of, so me and Miriam, we are in the client onboarding space of JPMorgan Chase, and of asset and wealth management division. So what we deal with a lot is with risk management and credit executives and people who are onboarding high risk net worth individual clients. And we wanted to always understand when these clients are investing, their investment behavior. So improve their management and monitoring of these clients, and so that we have more prioritization in terms of the monitoring efficiency, and how we can also prioritize their stock market investment strategies. So, and that is why this particular project is of importance to JPMorgan Chase, even though we are primarily using, outside, the students primarily used outside data, publicly available data for this project from Kaggle and Yahoo Finance and so on. JPMorgan Chase's main focus is on developing human-centered AI, and how we can use human in the loop also to make to deliver investment strategies for by leveraging the predictive models that we are showing here or others, and give investment solutions to clients. So this is one of the this is the basic framework of the deep learning based stock prediction model that we are proposing here, is that we are using the stock market data, the time series data here, and we are also using the option related, the volatility or the strike price data. And from there, what we do use is the Black-Scholes model of option pricing that many of you have probably have taken already financial modeling classes and are familiar with this kind of literature there. So there is there has been in literature some work where people have combined Black-Scholes option pricing models with uh, predictive modeling, and which is what we have kind of we have uh, modified, and some of the students they have developed on. But what we are also trying to do is uh, do more of daily or hourly based predictions, like on various time scales we are doing the predictions, and then furthermore use other more complex kind of algorithms into that. And from there we are implementing LSTM kind of models, machine learning or DL models, and then the other set of models that we are using is the ARIMA or FP profit kind of models, and how we can get a trends, specific trends of the uh, uh, stock market. So this is the now for data set initially that was being used here. Uh, so mainly we are using the Dow Jones kind of stock data. This is the Nasdaq closing price that it is predicting for the next 10 days, and the trend data is of 2024 that we are showing here. But initially we started our model with Dow Jones stock data from 2014 to 2024, so 10 years of data, and it aggregates over top 30 prominent companies. And all this data was fetched from the Yahoo Finance website using their APIs. And then what we did was a rolling average calculation there to get the trends. But here, apart from those basic analysis, we furthermore used ARIMA or an FA profit versus LSTM based models. And what they did was calculate the basic metrics here: mean square error, root mean square error, and mean absolute error or symmetric mean absolute error, and so on. So we also found that it is pretty, it is better performing when it comes to FB profit a little bit compared to ARIMA and LSTM. But this is too soon to say which is the best. This was just one of the preliminary analysis. And then based on that preliminary analysis, we wanted to complicate the model further. And we did some literature review, and we found that the artificial rabbit-based optimization of the obviously there's a lot of work happening in traditional LSTM-based models, and we didn't want to just we just wanted to use the traditional LSTM model as a benchmark. But then apart from that benchmark, how you can combine with artificial rabbit-based optimization algorithm with this LSTM model. And so this is one of the algorithms that have been proposed by Wang and his collaborators in their paper. And then in that LSTM model, the mean variables, certain features were selected based on their ability to capture certain sequential dependencies in the data. That is the close price, the call price, and the put price. So this kind of information is coming more from the financial modeling part. And the close, let me define what is a close price. The close price is the closing price of the stocks, which mainly would be the target related feature. The call price is more calculated using the Black-Scholes model. So that is the call call options theoretical price. And then we have the put price, that is also the theoretical price for the put options. So on the basis of that, here we are showing that in this LSTM RO-based model, what we calculated was MSE, mean absolute error, and symmetric mean absolute error, and of 30 stocks, and compared that with the DNN and LSTM-based models. And this artificial rabbit-based optimization has two stages. One is the detour foraging, the exploration, and the other is the exploitation, the random hiding. This is similar to reinforcement learning does. So in reinforcement learning, like many of the people here are computer science people, right? So what we do is more of a balance between exploration and exploitation. So we wanted to explore a computational domain and then take the best actions from those computational domain and then exploit those actions. So that is similar to that, the artificial rabbit-based optimization. It is a balanced trade-off between the exploration, that is the detour foraging, and the random hiding, that exploitation. And this strategy is coming based just by studying the behavior of how rabbits go and burrow holes and hide out from predators, right? Based on the same strategy in nature, people develop this algorithm, and we adopted that well. So, as the Chinese idiom says, that rabbits do not eat the grass near its own nest. So it's the same strategy that they use. And one important part here is that we have to optimize also the hyperparameters in this LSTM model. So in this hybrid LSTM model, that optimization took a long time actually for them. So this LSTM arrow-based model parameters are this. We have certain input variables, number of input parameters is 20, and then we have a dense layer, one dense layer, then there's a dropout dense. So it is around like 5 layers, we could see, around 3 LSTM layers, one dense layer, 2 dense layers, and one output, I think it's around 6 or 7 layers. And the number of neurons that was varied in this hyperparameter tuning is from 1 to 20. Layers were 0 to 1, and then these were the various optimizer algorithms: AdaGrad, AdaMax, stochastic gradient descent, and so on. And the learning rate was also reduced from 0.01 to up to 7 decimal places, and so on. So this is interesting. That was interesting in our aspect of how granular we could, or how precise we could actually train the model on. And the way the LSTM RO was trained it was trained on 10 years of Dow Jones data, like I mentioned earlier. The paper used for around iterations of 50 and population size of 50. What we did as a little smaller, population size of 10, and number of iterations with 25. And the results already started converging at 10 iterations. And for each combination of hyperparameters, also careful cross-validation was being used. This was some of the LSTM arrow-based results. So here, what was done was that it was compared among IBM and then Apple stock and then some other stocks. So here it is being shown that the actual values and the predicted values are pretty close in most of the models, which gave us further confidence on the way this model could be further used. Then it was compared with some of the benchmark Dow models, Dow Jones models, and it was shown that some of the trigger models of LSTM RO, LSTM Gaussian mixture models, and LSTM 1D, 2D, 3D, and artificial neural network models, and it is showing the mean absolute error of all these models for various stocks. This helped us actually benchmarking our model further. And some of the improvements that was being done is because this current model is also prone to overfitting. It is memorizing a lot of the previous prices data, but actually cannot generalize on different trends in the stock price or unknown stock prices. Then one solution was to add an option related data as another feature. And that's how the Black-Scholes option pricing model came into play, because so that we can reduce the model's dependency on historical price as only factor, and volatility could be used as an important hyperparameter in the model, so that we can actually predict the stock related to market crash or market uplift and so on. And this was some of the fit between the actual and the predicted values here. Then just giving an idea of what the Black-Scholes option model entails. So we have the various equations, various governing equations here, which involves the stock price, the strike price, the risk-free interest rate, time to expiration in years, and volatility of the relative price. And what it follows is a cumulative normal distribution function here in the model. So that is the main governing equation for the Black-Scholes option pricing models. And these are the various historical options data by the Black-Scholes model. So these are the open, high, low, close, and volatility, strike price, and call price, and put prices data. This result kind of shows the enhanced LSTM, that is with combination with the Black-Scholes option pricing model, and how it has reduced the distance between these two compared to a normal LSTM model, or even it is even supersetting the performance of the LSTM auto-based models. So the Black-Scholes option pricing based models in combination with the LSTM model and auto model is better than a normal LSTM or a normal LSTM auto-based model here. And then this was further extrapolated, as I mentioned, about hourly based data. How if anybody is going into more of options kind of trading or day trading and so on, then the hourly data is very important too, and how we can compare the mean from hourly versus actual daily close is being shown here. And then the box plot is showing the covariance coefficient of variation in the data. And the variability of the data isn't actually big within one day. Around 2% maximum is being shown here. So like the coefficient of variation for each day was calculated based on the ratio of standard deviation to the mean. And it kind of shows the variability in the data. And we show that there is very less variability here. So then now I will let Haunan speak a little bit. I've changed the slides a little bit here, but what we wanted to also investigate is a little more state of the art kind of work. So I forgot to put the reference here. This is a paper actually in Nature Machine Intelligence, which came into limelight a couple of years ago when me and Miriam, we were visiting a conference in finance, and we saw that a researcher from MIT was presenting this paper. And we had this idea that, okay, how we can implement this, because now they have launched a company also now on liquid neural networks, and got a lot of venture capital. But we had this idea to kind of implement that in stock market prediction. So kind of saw that our bright collaborators to see how they can implement that. So I'll let Haunan speak a little bit and explain further.
All right, thank you, Super Brother. Can we get to the next page, please?
Yeah.
Yep. So although we had a huge improvements on LSTM, and we still wanted to explore other models as well. So Super Brother once told me that there's a deep learning model called Liquid Time Constant Network, also known as Liquid NN, and it was developed by Rami Hassani, and that guy, like Super Brother said, later founded a startup company called Liquid AI. It's literally just based on this model. And the original version of Liquid AI is open sourced, and you guys can look it up on the GitHub. And the model was built on a recurrent neural network with some modifications, like they replaced the static hidden state formula with ODE to capture the dynamical system varying with time. However, as you can see here, it does not perform well on our data set. Like in the graph, when you see the training data set, it has a good performance, but when you take a look at the testing data set, it has a relatively poor performance, and that's a clear indication of overfitting. And next page, please.
Mm-hmm.
So why is the model not working on our data set while others found a company on it? So here are like two major problems that I can think of. The first one is that Liquid NN, unlike LSTM, it struggles to overcome data bias. So the stock price 10 years ago is much lower than it is now. So that's what we call data bias. For LSTM, it weighs more on the recent data, so it can overcome this bias, and that's what LSTM is all about. But for Liquid NN, it has a recurrent neural network structure. That means it is prone to be affected by old stock prices. And the second problem is that the model itself is too complex, where complex models are either too like cause overfitting issues because it memorizes the data. And the solution we came up with, and that's a thing that I'm currently working on, is to check the stationarity of the data. Data is said to be stationary if its statistical properties like variance or the correlation does not change over time. And we kind of ignore this step earlier because LSTM does not really care about stationarity. But now we encounter a problem with liquid AN, and that might require some changes in our original data. So we have to do it right now. So if the data itself is stationary, that means our data is good enough. So there must be something wrong with the model complexity. We can somehow reduce it. And then we can also add some feature engineering to provide more insights for the model. And if the data is non-stationary, that means its properties do not change over time. So we can like replace our 10 years daily data with probably 1 year's minute data or even 2 years daily data. I mean 2 years hourly data so that we can reduce the data bias that I mentioned before. And hopefully we can get Liquid to work as well. And besides the work we have done so far, you guys might want to further develop it since stock market forecasting is an everlasting problem. It has been here like since the first day the stock market was created. So therefore, I'm offering other strategies that you guys might be interested. So first of all, you guys want to explore like new approaches such as predicting the market trends, like the up and downs, instead of predicting the close price like we're doing right now. And second thing is that you can incorporate additional data sources, like you can perform a sentiment analysis on like on a YouTube page or on an article, and then make it a sentiment index and include that as a column to your data side. And that's another approach to do. And for third one, I think this is the hardest one, but it will be definitely it will be the most efficient one that you can develop a brand new model specialized for stock market forecasting. And I know there are like many brilliant minds here in this Zoom, and I definitely look forward to hearing from you all in the future. And I think that's pretty much everything from my side. And Sparta and Mary, you can take it from here. Thank you.
Right. Yeah, I wanted to explain this slide a little bit. This is from the original paper. Thanks, Haunan, for interjecting and explaining a little bit more and giving more context to the problem. But this is the original liquid neural network. The main idea is that how we can simulate the concept of the postsynaptic neuron here and solve this in a closed form, this neural network problem. So this equation is the governing equation here from the Nature Machine Intelligence paper by Hassani. Is where xt is the postsynaptic neuron's potential. Synaptic reversal potential is given by A. Synaptic release nonlinearity is given by the F function, and the postsynaptic neuron's time constant is given by tau. And this liquid neural network, the main advantage is their adaptability to changing input patterns, that it can dynamically adapt to varying data distributions. So that means when you are actually having a live forecasting model, with live data for the stock market prediction, then with a liquid neural network, it is easier because you can actually the model can dynamically learn from the data coming through. And also well suited for non-stationary data, because in one comment, like Haunan was mentioning, that he's actually for now looking for stationarity in the data, because all the other models so far, ARIMA and all the LSTM RO-based models, they will always have certain knowledge for stationarity of the data would be required. But here, even with non-stationary data, the liquid neural networks can adapt really well. The liquid neural networks also works well against any kind of noise and input variations. So because it is more like a fluid-like structure. So when it comes to machine learning model explainability and generalizability, then liquid neural networks actually really helps. And it also, when we talked about LSTM RO-based optimization technique, we also mentioned a lot about exploration versus exploitation trade-off, and like in kind of strategy in reinforcement learning. So liquid neural networks actually helps in encouraging, giving more flexibility in the exploration space in the network structure. So that exploration strategy, exploration will be really high in the exploration trade-off to solve more complex problems. That has been so far the talk. If the GitHub link is open, I will try to show. Let me see if I can open it somehow. It was open. I had opened it, but then I think I lost the GitHub now. But let me see. Yeah, I mean, this is just the no, this is not the one. How none you don't have the GitHub open, right?
Oh, wait a sec. I think I opened it.
I think I opening the wrong link every time. Because there were two groups. You can find. No, I can't somehow get. No, I somehow can't find it now. Yeah, if
I
you
sent
have
you over the link in the chat.
sent it over the link.
Mm.
In my where in email?
In the Zoom.
In the Zoom.
chat.
Okay.
Yep.
Okay, Zoom chat. Okay. Okay. Give it a minute. So yeah, this is the GitHub link for the project. So in any case, people have more questions on the code base and so on, they can actually get more understanding. But this is the initial, say, exploratory data analysis that was being done on the various rolling statistics of the data. This was the volatility plots that I did not show in the slides a lot more. This was some of the NASDAQ volume over time plots here and how the adjusted close prices, how we can show some of the outliers and any of the daily return distribution and so on. And this plot was showing the option price versus strike price kind of plot. So this exploratory data analysis plots I wanted to show a little bit because we did not, show that much. And then with option pricing model, this was some of the ML models prediction we might have already saw, but this is the code base. And they wrote pretty well actually because they did it more in a functional way so that people can actually use in a very modular fashion. But yeah, these are some of the other results to kind of show around. But yeah, and yeah, that's all from our side. Miriam, do you want to? Yeah, we can take questions, and then at that time, I think Miriam will speak. Yeah, that's all from our side. Any questions or comments and so on?
If anyone has a question they just want to ask, feel free to unmute yourselves and ask. We did receive one question in the chat, but Ryan, go ahead if you want to ask your question.
Yeah, hi, thank you for the presentation. My question is, what was your rationale behind training on Dow Jones data instead of like maybe the NASDAQ or the S&P?
Yeah, we wanted to find a benchmark. I think most of the papers were published on Dow Jones data. That was one of the main rationales. So we wanted to kind of see that the model is performing well against the benchmark data, benchmark models, right? Haunan, do you want to add anything here?
Yeah, and also the price of Dow Jones is much lower than NASDAQ. So when you train the data, you have to like transform it to within a scope from 0 to 1. So if you are working with large numbers, when you convert it back, we'll have like our large errors, and we do not want that. So we chose a relatively small stock price, which is Dow Jones. And also, as Superbird said, it has been used as benchmark in lots of papers. Yep.
Okay, thank you.
Yeah.
The question in the chat, and feel free to chime in if you want to answer this or ask this yourself, but Hernan asked, would you please elaborate on the features you add to the model from the Black-Scholes calculation?
Yes, some of the features that was being used are the variables which are defined here. There's the risk-free interest rate, stock price, strike price, call price, put price, and then some of the variables related to the volatility of the price range. Yeah, Haunan, do you want to add a little bit on the derived features apart from these principal features?
Yeah, I think we added the call option price, put option price, and also the volatility from the Black-Scholes model into our original data set. Yeah.
Okay, so it's the same. Okay, and call option, put, and volatility. Yeah, those were the features.
Thank you.
Yeah. Any other question or comments? That you are possibly facing in similar kind of work?
Just like to comment, what a great presentation from both of you. So thank you so much for taking the time to explain your projects today.
Yeah, thank you so much again for all the guests and all the organizers here and giving us the opportunity to present here.
Of course. Okay, does anyone else have any other questions? Obviously, we are able to reach, Mariam and Sabrata from time to time. So if any follow-up questions, feel free to reach out to me and I can get you in touch. So
Yeah, and yeah, feel free to reach out to us. Yeah, and Alexis and Joy too. Yeah. Okay.
there
Thank
are
you.
no other questions. Thank you so much for joining us today. So stay tuned for other iCubed seminars. We have a few coming up, including like Johnson & Johnson. So yeah, thanks for joining us today.
Thank you so much. Yeah.
Okay.
Thank you.
Bye.
Thank you.